So for this section, we're going to start section 4.1 by introducing a fact about where a function is increasing or decreasing. So we say if f prime of x is greater than 0 on some interval a to b, then f of x is increasing on that interval a to b. Meaning, if your derivative is equal to positive 2 between the x values 1 and 4, then that means between the x values 1 and 4, your original function is always increasing. Your graph would look like it's sloping upward. If f prime of x is less than 0 on some interval a to b, then the original function f of x is decreasing on that same interval. And if f prime of x is equal to 0 on that interval, then the original function has what we call a horizontal tangent line. It means that it's neither increasing nor decreasing. It just looks like a flat horizontal line. So just to cover that one more time, if your derivative is positive, that means that your graph is increasing on that interval. And if your derivative is negative, it means that your graph is decreasing on that interval. Remember, we said that a derivative represents the slope, so obviously if your slope is negative, your graph has to be decreasing from left to right, and if your slope is positive, it has to be increasing from left to right. From here, we introduce another fact or definition that says a partition number or partition numbers are the only x values where f prime of x can change from a negative to a positive value, or from a positive to a negative value. With that, we say that they're found by setting the derivative f prime of x equal to 0, and also finding where the derivative f prime of x is undefined. An easy way to go about this is to always set up your derivative in fraction form. So notice I've written f prime of x equals g of x over h of x. That literally just means that your derivative is some value over another. You have a fraction. So it could look something like x cubed over x plus 1. So this is saying to find these partition numbers, set the numerator equal to 0. So in this case it would be set x cubed equal to 0. And set the denominator equal to 0. That'll tell you where it's undefined. So you would set x plus 1 equal to 0. And when you solve for each of these equations, it will give you all of the possible partition numbers, or all of your partition numbers, given that original derivative. The last thing to note from here is a process we have to find where a function f is increasing and decreasing. So we're going to put together the last two facts that we introduced to create this process. So the first thing we have to note is to find f prime of x. To start this process off, we always have to find our first derivative. And then from there, we are then going to use the first derivative, so use f prime of x, to find the partition numbers. So remember, we just said to find the partition numbers, you take the first and the second, the first derivative's numerator and the first derivative's denominator, the top and bottom of your fraction, and you set each of them equal to 0, that will give you the partition numbers. And now from here, we test a value to the left and right of each partition number in our derivative. And when we do that, we are checking to see whether those results will be greater than 0 or less than 0. And that goes back to the first fact that we introduced. Remember, we said if the first derivative is greater than 0, then that means the function would be increasing on that interval, which is what we're looking for here. And if the first derivative is less than 0, then that would mean the function is decreasing. So, combining these two facts that we introduced just a moment ago, we now have a process to find where the entire function is increasing and decreasing. So we'll start by trying out an example. For this example, we have f of x equals 8x minus x squared. And we want to find where this function is increasing and decreasing. So remember, our first step was to find f prime of x. The derivative of 8x is just 8. Remember, whenever you have any constant times x, the derivative is just that constant. Minus the derivative of x squared. Remember, you multiply the exponent out front and subtract 1 from it. That gives us 2 times x to the first power, which is just 2x. And now that we have our first derivative, we can set it equal to 0. And we set the denominator equal to 0. Now you might be thinking, what denominator? Well, remember, if you want to turn anything into a fraction, you can technically take it. So I'm going to write this off to the side, 8 minus 2x. You can always take it and put it over 1. So in this case, there is nothing that is going to make 1 equal 0. If we were to set 1 equal to 0, that's impossible. So whenever you just have a regular polynomial, you do not have to worry about f prime of x being undefined. Remember, we said when you set the denominator equal to 0, you get where f prime of x is undefined. That cannot happen in this case. So we just have 8 minus 2x equals 0 to solve for. The second equation, where f prime of x is undefined, cannot occur. So we begin solving this. We'll start by subtracting 8 from each side to get negative 2x is equal to negative 8. And then dividing each side by negative 2, we get x equals 4. So x equals 4 is our partition number. It's our only one. So the last step said we had to take this partition number and any others that we could find. In this case, there's only going to be this one. And we have to test a value to the left and right of each of them. So we can do this two ways. The first is by making a number line. The second is by making a table. So I'll go ahead and start this example with the number line. We are testing around x equals 4, which means testing a value to the left of it, we can pick 3. To the right of it, we can pick 5, and we're testing these values again in our derivative f prime of x. Remember, if the result when we plug these values in is negative, then the original function is decreasing on that interval. If it's positive, the original function is increasing. So, when we plug 4 into the derivative, we already know what the result will be. We said when x equals 4, that's when the derivative is equal to 0. That's the equation we solve for. So we know it will be equal to 0 here. So from there, we'll test x equals 3. If you plug 3 into 8 minus 2x, you get 8 minus 2 times 3, which gives us 8 minus 6. That's positive 2. And we'll come back to that in just a moment. Now we'll plug in 5. We have 8 minus 2 times 5. That leaves us with 8 minus 10. That's negative 2. All we care about is the fact that we got a positive result and a negative result. That tells us that on the interval containing all numbers to the left of x equals 4, the first derivative will always be positive. So let's think about that. Let's say f is increasing on what interval? Well, no matter what number we pick to the left of x equals 4, the first derivative will always be positive. This 3 was just one easy value to plug in to show that everything else to the left of x equals 4 will give you a positive result. So, what's the furthest number to the left of x equals 4? The furthest number would be negative infinity. And now we go all the way until our first derivative is no longer positive at x equals 4. The first derivative is now a 0 value, which means it stops being positive at x equals 4. We cannot include it, so we put a parenthesis. From there, we say f is decreasing everywhere that the first derivative is negative. Well, every number to the right of x equals 4 gives a negative in our first derivative because of this negative 2. So we'll say starting at x equals 4, and again we put a parenthesis, because you can never technically say you're decreasing or increasing at one exact value. So there will always be a parenthesis here, never a bracket. So starting at 4, we go all the way to the right. Every value in our derivative will be negative. So 4 all the way to positive infinity will give us the values where the function is decreasing, because those are all the values where the first derivative is negative. And this solves the problem. We have now found everywhere that the original function f is increasing and everywhere that it is decreasing. At this point, we're going to go through one more example. This one is slightly shorter. We have f of x equals 4x minus 3. And again, we want to find everywhere that the function is increasing or decreasing. At this point, for your best success at learning this, I suggest that you pause the video and do your best to try this problem on your own. Feel free to rewind it to look at what we did in the last example. And now we're going to try it together. So, remember the first step? Find f prime of x. F prime of x, the derivative of 4x, is just 4. And the derivative of minus 3 is just 0. So f prime of x is equal to just positive 4. Now this one might seem a little bit tricky, but it ends up working out rather nicely. We have f prime of x equals 4. If we were to rewrite this as a fraction, like we did in the last problem, we would put it over 1, as anything is the same thing as itself over 1. And with that, we now set the numerator and denominator equal to 0 to solve for our partition numbers. Now notice there are no partition numbers in this case. 4 can never equal 0, and 1 can never equal 0. So what does that tell us? Again, there are no partition numbers. Nothing will make either of these values equal 0. So we immediately go to our number line or table. As I said, I would make a table in this problem. So we have x and f prime of x. And because there are no partition numbers, we don't have to test to the left and right of anything. We just test one value. One value will tell us what's happening for the entire graph. If you always remember, if you do not have a partition number, then one value will tell you whether the entire function is increasing, the entire function is decreasing, or it's neither increasing nor decreasing. We can pick anything we want, so I'm just going to go ahead and pick 0, as 0 usually ends up being one of the easiest things you can pick. We are plugging it into the first derivative. So plugging 0 into f prime of x equals 4, there is nowhere to plug 0 in. The result is just always equal to 4. Again, I apologize for the confusion there. So, what does that tell us? The derivative is always equal to 4. No matter what x value we pick, f prime of x will always equal 4, which means f prime of x will always be greater than 0. So f is increasing no matter what x value we pick. So we say f is increasing on the interval -infinity to +infinity. No matter what x value we pick, it will always be increasing. It will never be decreasing. Now the logic behind this. Think about what this original function looks like. 4x minus 3. That's just a line. If you were to graph this, I'll do this off to the side, it would look something like this. Notice, starting from left to right, the graph is always gaining in y value. The y value is never suddenly going down. That means it's increasing from negative infinity all the way to positive infinity. So this covers partition numbers and finding where a function is increasing and decreasing. I suggest checking through some other videos in section 4.1, which will provide even more detailed examples on this topic.